I think
All right, welcome back, everyone. We're going to have a brief panel discussion. As is probably obvious, the panel is sitting over here, and we only have this screen on. So if your vantage is a little bit hard from the other side of the room, you can maybe make your way across. So to start, I'm going to quickly introduce the SkAI Institute for those of you that have not been here or don't know much. We're very excited to be hosting you today. As you know, because you are in the building, the SkAI Institute is here within the Hancock Center, and you are here for our first look with Rubin event, which again you also know because you are here. Very briefly, just to get into a few of the numbers here, the SkAI Institute is part of a national initiative to develop AI centers to solve challenging problems across a wide variety of fields. 2 years ago, there was a call that was made to create AI centers specifically to do astronomy and astrophysics. And so researchers, primarily from Northwestern, the University of Chicago, University of Illinois Urbana-Champaign, came together along with many researchers at several other universities across the country to propose for, and eventually we won, the SkAI Institute. And it's a very, very large team. There's already 100 people associated with the Institute, but we expect that number to grow as more students and postdocs get interested in working on this particular science. There are 25 total institutions involved. So while the Institute is led, like I said, by Northwestern, Chicago, and UIUC, there are many other places that are involved. We have many partners in industry. So NVIDIA, they come to mind first because they are the world leaders in building the chips that do AI, but several other industry partners as well. And our science is organized into 3 different research pillars. Very briefly, this is roughly analogous to the scientific method. So we are using AI to develop simulations. This is the theory component of the project, which will then tell us about what we expect to see in our observations. So this is the data that's coming from surveys such as Rubin, which we just heard a whole lot about. And once we get this new data, we have to ask new questions of the universe. And so we build new telescopes, new instruments. This is the instrumentation pillar within SkAI. We have many different events throughout the year. You can sign up to be a SkAI member if you are at any of the member institutions. And we're very excited to, again, be hosting you in our physical space for our first event and hope to see all of your faces again in the future. So one more time, right? Here's Rubin. Here's not what the sky looks like if you're there at Rubin. Here's what the sky looks like if you have a long exposure with your digital camera. But we're going to be talking about the incredible science that can be done with this particular facility today. And we have a panel of experts, all senior personnel within SkAI, who are going to start by telling you a little bit about the research that they hope to do. We'll then ask a few questions of the panel, and then we'll open it up to a Q&A in the audience. Okay? So I'll start by introducing our panel. Online, we have Travis Rector, who's a professor at the University of Alaska Anchorage. We also have Gautham Narayan, who's a professor at UIUC, Charlie Kilpatrick, who's a faculty member at Northwestern, and Chihway Chang, who is a professor at University of Chicago. So I'm going to hand things over to them now to introduce their research, starting with, oh, sorry. I wanted to emphasize for everything one other point. I have quite literally spent my entire life as an astronomer waiting for today. This is not a joke. I was positive, I misremembered, I was positive the very first paper I wrote as a PhD student actually had a reference to LSST. I went back and reread it. It did not, but just a couple years into my PhD, and I won't say the year, but you can read it, it's on the screen, I was writing about LSST and how important it would be for our understanding of the time variable universe. I also highlighted in that particular paper that there were going to be challenges that we needed to solve before we could deal with the giant volume of data that we're going to be getting from Rubin. And in fact, the work that I am doing in SkAI is related to these sentences I wrote as a naive, not very intelligent graduate student over a decade ago. All right, so this has been a very long time coming. In fact, for some of you, before you were born is when the planning for this project started. And so this is an immense and very big deal that we are now here. Okay, with that preamble out of the way, I'm going to pass it over to our panel, starting with Travis for a discussion of the work that he is planning to do with Rubin.
Well, hi, everyone. I can one-up you. I was actually a postdoc at Kitt Peak when the first discussions about LSST were first coming about. And so it is a profound moment for many of us to finally be at this moment. I actually got to do a sabbatical in Chile back in 2019 and was there when the mirror M1, M3 mirror was delivered. So just very quickly, so my main interest in LSST is creating opportunities for undergraduate research. Over the years, I've worked on many different projects that are well suited for undergrads, in particular, doing what are called CIERAs. These are curriculum for undergraduate research experiences. And two of the projects that we've done, one is finding classical novae in M31, which is traditionally quite difficult for computers to do because of the complex environment in which the novae are located. And then recently we've been doing a project, a citizen science project with Zooniverse, where we are having people look at images of star-forming regions to look for Herbig-Hera outflows, which have distinct color signatures as well as morphologies. And both of these are examples of projects that have been really well suited for people who lack this astronomy expertise, but our brains are just hardwired for being able to detect these sorts of structures. And it's an exciting time to see how AI will be able to assist us not only in finding these sorts of objects, but also assisting those who wish to be part of this process, whether they be undergrads or citizens. And I'll also mention that I'm part of the team that created the first look images that you guys got to see today. I've had them on my laptop for a while now and have just been so excited to share them with everyone. And so it's an exciting time in the role that AI can play in image processing and visualization, but it's also a cautionary time as we start to see more and more fake images of everything, including space, online. And so there's an interesting question about how do authentic images like those made by Rubin, how will they stand out against the backwash of AI images? So that's a little bit about me.
Thank you, Travis. And next, I'd like to hear from Chihway.
Cool. Hi, everyone. I'm Chihway. Okay, so my LSST journey, probably similar to Adam. I did my PhD 2007 through 13, and I worked basically full time on LSST. I tested some of the earliest CCD detectors in the labs, and they were not very good. So it's great to know that N years later they work great now. After that, I did a little bit work on this precursor survey to LSST called the Dark Current 2 survey, and that's kind of finishing up. But from that, I really saw the power of having a generic survey and how much people can use the data to do things they have not planned for. And I think that is a real kind of opportunity for LSST that we can say all we want to do, but what we actually will do is like beyond our imagination. And I think that's the part that really excites me. Okay, so the things I actually do in a day-to-day life, I use the large-scale structure to study the content and the history of the universe. I'm an observational cosmologist. So a lot of what Aaron said in his part of the interview, that's basically what I do. I do a lot of statistics with this like big set of data. And I think there is where I'm excited about AI coming in and solving some of the hard statistical questions for us, or speeding it up, or sampling parameter space we did not think we could sample in a traditional kind of MCMC world. So if you look at this, that's basically sort of what I do, kind of trying to map this large scale structure in the universe, which is the backbone of everything, using different galaxy products. Another thing I'm excited about is combining this data set with other angles of looking at the universe through different wavelengths and eras of the universe, and kind of piecing together the overall history of what we're coming from. That's what I do.
Thank you. And next, I'd like to hear from Gautham.
Sure. I'm Gautham Narayan. I'm one of the deputy directors for SkAI. I, like the others, have been working on LSST for a very, very long time. I checked with Adam, and in fact, I ended the very first paper that I ever wrote with the word LSST, promising remarkable new transient discoveries, which we've been doing with precursor surveys such as the Young Supernova experiment. The sort of things that I'm trying to do are find large populations of transients that you might have heard about from Shelko, so large data. Combine the data from Rubin with Euclid, with gravitational wave observatories, with astroparticle observatories to get multimodal data to really understand the physics of these transients. And the particular transients I've been working on from grad school on are type 1a supernovae. These are the rats of the universe, if you like. They're like 70% of all of the supernovae we find, but they are standardizable candles, and which means you can measure the distances and use them to measure the accelerating expansion of the universe. In fact, I can tell you that Rubin has seen its very first type 1a supernovae. So on that little left inset is some observations from DECAM that we took at the same time as the Rubin commissioning program in October to November. And that is by a type 1a supernovae, 2024 KEFJ. And so we'll find very many more of these things with Rubin over the next 10 years, and hopefully have the most precise measurement of dark energy, combining what I do with what Chihway does and others work on as well.
Okay, and then finally, Charlie.
Yeah, hi, I'm Charlie Kilpatrick. As Adam mentioned, I'm research faculty at CIERA at Northwestern. I'm also a member of the Transient and Variable Star Working Group in Rubin. I began my sort of scientific journey in space, studying massive star explosions in our own galaxy, and then much more recently started working on a lot of the precursor surveys, including the Young Supernova experiment with Gautham to LSST. My interests are mainly in massive stars and sort of the progenitors to a lot of the explosions that other members of the panel study. There's going to be millions and billions of these massive stars just in the LSST images themselves. But even though LSST is going to give us very exquisite resolution with its active optics system, we need new techniques to be able to deblend and detect these sources in the really crowded extragalactic environments where we're going to be finding them. And ultimately, I'd really like to map the evolution of these stars, which we're going to find in all sorts of unusual configurations, to the explosions that we're going to be seeing out to high redshift. And sort of my holy grail for LSST, and someday I think we'll do it, is find a massive star right before it explodes and be able to observe it, sort of catching it in the act.
All right, thank you all for that introduction. So as a first question to the panel, I'd like to start, Travis, with you. You mentioned that you worked on building these first look images that we all got to look at just a few moments ago. Can you tell us a little bit more about that process and what it was like working with the early data from the telescope?
Well, it's really been an absolute treat. I mean, everything about Rubin has performed at a level that exceeds, I think, even the best hopes of the team from the get-go. So we actually had an accelerated timeline in as much as we anticipated initially it would take longer for us to get good data. But it really is the best ground-based optical imaging data I've ever seen before. So we made two images. One is of the galactic field M8, M20, and M21. I mean, it's just amazing all the objects are in a single image. And then we had the deep field centered on M49. And the M49, the deep field image, has about 1,200 visits, so 1,200 30-second exposures in UGRI, and represents the depth that the LSST will achieve in the 10 years of operation. And really, it's just been an incredible treat to work with the data. I encourage everyone to download the full resolution images and just pan through them and see all the incredible stuff that's in there. I had the privilege of helping with the color compositing and also the final cleanup. And so for fixing any residual cosmetic problems like CCD bleeds, chip gaps, etc. And it's just been amazing to step through it just portion by portion and just seeing all the incredible galaxies that are in there. And as Željko mentioned in the press conference, I mean, we're really at a point now where the data are so deep that you're running out of black sky. I mean, you're getting to the point where it's just an endless sea of galaxies, and it's really been stunning. So our team consisted of about a dozen people who represented all the different aspects, from the data pipeline to the image, to the observations, to the final image assembly. And it really is just incredible how much skill is how many different skill sets you need to create these sorts of images, and it was just a sincere pleasure to be part of that process.
Okay, thank you. Chihway, you mentioned in your answer that you're interested in not just using Rubin, but connecting this to other facilities as well. Could you tell us a little bit more about some of the other observatories that are out there and how they'll complement the data that Rubin will get for the science you're interested in?
Yep. So let's think about it. So I think the part that I'm mostly familiar and interested in is combining with CMB telescopes. So the thing that's currently happening is the Simon Observatory, which some of you have heard of. It's down in Chile, and it's doing a similar thing as Rubin, just in a millimeter wavelength, swapping out like giant parts of the sky. So that and Rubin is a good, very good match. That data is coming in, I think, in the next couple of years, and I think that combination will really allow us to look at kind of solve these problems of where is gas distributed around galaxies and how that may or may not bias our cosmology. So that's a technical detail, but that combination is really going to help us a lot. Another telescope, South Pole Telescope, is a similar data set down in the South Pole. And I think they have similar but complementary kind of features compared to Simon's Observatory. The other combination I think it's very interesting for a lot of us is combining with DESI, so this spectroscopic instrument. So it's still optical imaging, but spectra. So that allows us to know kind of both the redshift very well, and that's something Rubin doesn't do great. But aside from that, also kind of the galaxies and more detailed understanding of the types of galaxies. So I think those two combinations is what I'm like most familiar with and most excited about, but I'm sure there's a lot more.
Okay, that's great. And then actually, Charlie, I'm wondering if I could throw it to you. So we heard a lot about looking at light that's coming from outer space, but we also now, of course, can detect gravitational waves. So can you talk about how Rubin will complement efforts to detect gravitational waves and high energy neutrinos throughout the universe?
Yeah, of course. So first of all, Rubin is dedicating about 3% of its time in the survey to gravitational wave and other kinds of multi-messenger follow-up. So there are a whole raft of types of targets of opportunity that are being integrated into the system right now. And actually, if a promising gravitational wave event occurred and met certain key parameters that the TOO group has already outlined, today even Rubin could start observing and looking for counterparts to that event. So the key type of event we're mostly interested in is a neutron star merger, which would have a kilonova counterpart, similar to the one that we found in 2017, very close by in our own neighborhood. But because LIGO is now observing these events out much, much further as it gets more and more sensitive, we need telescopes like Rubin to be able to very rapidly localize them. So because of the very wide field camera that Rubin has and its slew capabilities and the nice filter suite it has, it's really almost a perfect instrument to be able to localize these types of events. Of course, there are other types of events that we're interested in the multi-messenger universe, like Adam mentioned, neutrinos and high energy particle events, black hole mergers. And one really important thing that Rubin's going to do is give us one of the best catalogs, really the best catalog ever of all the galaxies, stars, variables in the southern sky that we're going to need to be able to weed out sort of interlopers and pick out the right galaxies that we think are hosting these events. So these data products, both the TOO follow-up capability and the static sky science, I think, are going to be really key for multi-messenger science in the next decade.
Okay, thanks for that answer. We have a lot of younger scientists in the audience today who maybe have only written 1 or 2 papers that said when LSST gets here, it's going to be so deeply exciting. And then one of the things that we have a great deal of access to here in SkAI is a lot of compute resources, including at NCSA, which is co-located with UIUC. And so, Gautham, I'd like to throw my next question to you to ask, in what ways can students and postdocs prepare themselves to learn about AI tools in order to deal with this new incredible data set that's coming from Rubin?
Yeah, and there's no shortage of things you can do, as you've heard from the other panelists. When Adam says AI tools, don't interpret this always as purely convolutional neural networks or physics-informed neural operators or recurrent neural networks. I think it is worth exploring the data in many, many different ways. The way Rubin is sort of encouraging people to play with it is to make DP1, Data Preview 1, which is ComCam data, available within a week. So this is around 2,000 images, some of the deepest that you have seen of many, many regions, including the Euclid Deep Field South and the extended Chandra Deep Field. And that data set is relatively small, so it'll be available through the Rubin Science platform, but we'll mirror it at NCSA. So if you're in SkAI, you'll have access to it. It's only around 18 terabytes. You can take your favorite off-the-shelf AI model from Hugging Face or whatever you like, and try to deploy this on the data on June 30th when this data becomes unembargoed. And there's a lot you can do. You can attempt to, for example, extract photo Zs for all of the galaxies in Euclid Deep Field South. This is something that Charlie mentioned. Rubin will allow you to make some of the deepest galaxy catalogs out there. You can find transients in supernovae. Like I said in my intro slide, there are known transients in the source, known variable stars as well for folks like Adam. And as you saw from Željko's presentation, there's anything that you hope you can do on the full Rubin dataset. Remember, DR1 is a long way away from Rubin. You should be able to start doing on DP1, which is out in a week, and next on DP2, the science verification data, that survey will start essentially now and be released in April 2026. And we are going to be mirroring probably both of those things and giving you access to the GPUs at NCSA if you're a SkAI member to do whatever the heck makes you interested. And you should really feel free to experiment, and don't worry, you're not going to break anything. So try things, even if they seem crazy at first, because we don't actually know all of the things you can find in this data set. That's the whole point of it being discovery space.
Okay, thanks for that. I'd next like to ask a question of all of the panelists, and then we'll turn to the audience for a few more questions. But I'm curious, has the SkAI Institute changed the way in which you think about Rubin data at all and what's possible? And within that framework, what's the thing that you would be most excited to discover or find as part of your work within SkAI? Chihway, I'm looking at you, so why don't we start with you? Sorry to make you go first.
All right, that's a deep question. Let's think about that. So I do think kind of the opportunity of SkAI really brought some of the people I wouldn't think of talking to into our sphere. So statisticians in our same institute, I would not imagine kind of sitting down and having a serious conversation with them. And now it's kind of a regular thing we do. So I really thank SkAI for that. And I really think it allows us to think about problems very differently. So the particular thing I am interested that's hosted under SkAI, I think it might be a bit futuristic, but I think it's what LSST like. It is the thing that I think we want to aim for with LSST to really kind of harness the most of the information in the large scale structure. So the thing like I'm interested in is how to kind of reconstruct the large scale structure at its earlier stages. Like what is the distribution of dark matter that had evolved into what we see today? So in the past, we only been able to do this on a like a really rough level, on like very low order statistics. But I feel like with the advance of both AI and better understanding of statistics, as well as the data set, perhaps we can make headways there. I think mainly the thing I'm trying to get to is with LSST, like with this magnificent data set, if we're still doing exactly the same thing as what we did with the Dark Energy Survey, like that has finished taking data 6 years ago, that would be a shame. Like all this extra data, we should be doing something different. And I think that's what I hope to get.
Okay, great. Charlie?
Yeah, I think during the panel that we saw previous to this, there was some discussion about how the Rubin data set is so massive that really it's a matter of bringing scientists to the data, not just giving them the data and the tools. And really, I see SkAI as sort of an incubator for accelerating that process and sort of smoothing or greasing the skids a little bit. To make it easier for us to get to the data and the products that we need. So that's not necessarily just CNNs and sort of learning-based tools to classify things more rapidly, but really every process that Rubin is going to be doing, we'll have experts here who are going to be able to work with computer scientists and astronomers to be able to analyze SkAI data or Rubin data rather in new ways that no other group in the world is going to be capable of doing. So that's really what I'm the most excited about working in SkAI is sort of working with people who I've written papers with for over a decade now, but also reaching out to new collaborators at UChicago and all over Illinois. To be able to find new ways to really leverage this data set for my science and bring my expertise in time domain and massive stars and imaging techniques and astronomy in general to enable other people's science.
Okay, great. Thank you, Charlie. Travis.
I'll offer more of a philosophical perspective. Not to get into play the old man in the room, but when I first started in astronomy and CCDs were becoming a thing, there was a big question about how are we going to process the data from these instruments? I mean, how would we even store them? There was discussions of potentially storing CCD data on photographic plates because we just simply lacked the hard drive capacity to store the images that would be produced. So there's always been this struggle between the volume of data that's produced and the techniques necessary to store and process that information. And the same thing really happened with Rubin when the first realization that there would be 10 million alerts a day. How can you even possibly process that and wrap your mind around it? And it's just a remarkable confluence that AI in general and SkAI in particular is poised to be in this place to take advantage of what Rubin is going to produce. It's clear that AI is going to be an essential tool for us in interpreting and understanding what Rubin is able to see. And so it's a very exciting time in astronomy to see where this is all going to go.
Okay, thank you for that. And I guess by process of elimination, Gautham, it's your turn.
Yeah, so I mean, I hope folks have read the little book by Lyman Page, just 6 numbers that describe the universe. And I think the reason that it is just 6 numbers is we do, like Travis said, we simplify our data. We use data reduction. We compress things until we have a simplified spherical model cow model that we can compare against the observations. And the reality that we're seeing is that the observations are much more rich. There's much more that we could capture with our measurements now than can be described by simple 6 numbers. We don't want to just study omega matter. We want to, as Chihway said, combine Rubin data with SPT data to understand the gas around galaxies, but then also how is that gas getting blown out by supernova feedback, and how does that change over cosmic time? Cosmology is just a much more complex field than 6 numbers, and AI is finally giving us a way to combine these multimodal data sets in a way that we can actually do inference. AI fundamentally is a function emulator, and we're making it emulate more complex functions than we have been able to do with traditional techniques in the past. And so what SkAI, I think, is on the cutting edge of doing is being able to take real astrophysical survey data, put in physics-informed methods into these neural networks, get reliable uncertainties out of them, and instead of comparing them to just 6 numbers now, compare them to the largest galaxy n-body simulations that we have, for example, and see how the universe actually changes in our observations. Remember, Rubin is a movie in both time and space, and see how these compare to what we are actually seeing from the biggest supercomputers in the world. And so I think that's what SkAI is actually enabling, and that's the thing that's going to be different over the next 10 years, and how Rubin, I think, will take us beyond what was possible with dark energy survey and prior experiments.
Okay, thank you for that perspective. We have time for a few questions from the audience. I see a hand in the back. Yes.
I read an article interviewing Gautham Narayan from the LSST scientist and professor at University of Washington. And in this Atlantic article from 2024, he says that kind of unable to compete with the survey plan. And obviously the discussion we're having today says otherwise. So what has changed since then, or what was my misunderstanding?
All right, I'm going to briefly synthesize the question just so everyone online can hear. But the question was about TOO observations, which stands for time of opportunity. And so these are when you essentially say, even though the telescope is planning to look at some galaxy that's over here, some incredibly interesting phenomena is happening some other location on the sky. And so we're going to interrupt our plans in order to immediately go and observe this new interesting phenomena. And there was a long discussion, this is what the question was getting at, about whether or not this would be possible with Rubin, where for many, many years, the plan was that such observations would not be possible, but that's no longer the case. And I'm going to throw it to Charlie to give a quick answer for why this has changed.
Yeah, so that's right. LSST and Rubin have always sort of been, it's a survey that's balancing many different types of science. So that, sorts of things that Chihway and I study, even though they're, in some sense quite different from each other. The observing strategy that you can use to study them, there's a lot of overlap in terms of that. Now, TOOs that are, by design, probably the most disruptive type of observation that we perform. We're essentially telling the LSST scheduler that Fed was talking about on the previous panel that we want to stop everything that it's doing right now and slew to a different part of the sky and do something completely different. And you're right that, 3 or 4 years ago, that there was not a definitive plan to be able to execute that. But 2 scientists, Raffaele Margutti and Igor Andreoni, wrote a very compelling white paper that I participated in, arguing that there are certain modes of observations and gravitational wave follow-up in particular that are so high priority and have such buy-in from the community that LSST needs to consider doing this as part of its observing plan. And so in this white paper, we outlined the many different modes of TOOs that we hoped LSST would execute, and the collaboration agreed and set aside this 3% figure of its time. that it's now going to commit to following up sources in the future, but only if they fall in a very strict, essentially programmable set of criteria that we're going to follow to the letter. And that's really the reason why it's possible, because all of this can be executed mostly autonomously. There's still a human in the loop that has to vet the TOO and tell the telescope that this is what it's going to be doing. But by making it very automated, we've essentially simplified the process and minimized the disruption to other LSST observations.
Can I quickly chime in here as well?
Of course.
On the TO front. So on the commissioning side, I can tell you the TO pipeline has now actually been implemented. So the SIMA group that I'm the PI of has been able to send in LVK alerts from O4C into Rubin Observatory, into the scheduler. There is a plan to simulate a fake LVK binary neutron star event this coming week, such that it has some overlap with the existing decade pointing in the south, which is essentially most of the southern region covered by DES, plus Alex Wagner, one of our SkAI colleagues, big surveys. There's no U-band, not very much U-band. There's virtually no Y-band at all. But we can test this observation probably in this coming week, make sure it all works end to end. It doesn't actually disrupt the science all that much in the end, because the way LSST scheduler works, it measures metrics on the entire sky. So if you have more observations in a particular region, it weighs that and comes back there less in the future. So it doesn't affect the static sky. It does affect some of the other transient signs for a little bit. But remember, all LSST has to do is localize the transient, tell other telescopes where the binary neutron star's electromagnetic counterpart is. And then Rubin can stop looking, because you can follow it up deeper with something like DECCAM spending 600-second exposures rather than 30-second Rubin exposures.
Okay, thank you. Are there any other questions? Okay, we'll have one more question. Yeah. That's a wonderful question. So I'll repeat for those of you online. In brief, the question is, in what way will the data set that we have and the science questions that we're trying to answer in astronomy and astrophysics inform AI? How will we make artificial intelligence better by using this data? Anyone want to jump at that question? Chihway?
Right. So I think there are already examples that we know, like the questions we're interested in astronomy and cosmology doesn't fully fit into the framework that machine learning algorithms or techniques are designed for. So prominent examples are like uncertainty quantification. So I think very little machine learning usage outside of science care that much about your uncertainties. Like, we really need to know this at the level of a few %, right? So I think because that was not cared about in industry and other places, it's not as developed and not as like the algorithms and the architecture are not centered around that. And I think that is already an area where like we need better developments on the AI side to suit the science part. Similarly, I think the other, like the example I said earlier, the things I'm interested in is like sampling over 1 million of parameters. Again, for kind of industry purposes, people might do that, but not care about it that well, like how well the end result was. That's like how uncertainties are quantified in a certain parameter. Whereas in our case, I think we do actually care about that. Which if we talk to our stats colleagues, they they will pause and say, yeah, we don't think we have such a ready algorithm for you to use. We'll think about it. We'll think about like shortcuts and bypasses. So I think this is an example that it's feeding back to the type of the questions can trigger some development in the other direction. But I'm sure there are more.
Okay, thank you for that answer. As a last little note before we depart, if you've been very excited about everything you've heard about today, oh dear, no, yeah, here we go. It turns out that there is going to be data available from Rubin, Gautham mentioned this, exactly a week from today. And we're having another event here at SkAI where we will be exploring this particular data set. It turns out I'm a terrible panel lead. I never told you my name. My name, everyone, is Adam Miller, and I'm a faculty member at Northwestern University. And I'm going to be leading an event here in our space at SkAI where we look at this data as it becomes available. My people on the inside tell me that there is no official time when the data is going to become available. We are hoping that it is at lunch. That's the best guess right now. So at 11 o'clock, there's actually going to be a tutorial for how you get into the data and what all is in the data set. So we'll watch that together collectively. And then hopefully at about the end of that hour, the data will be available and we'll spend some time working in the afternoon. But you can RSVP for that event here. It's also announced in the SkAI Slack. If you're not a SkAI member, you can become a SkAI member. But we hope to see you at that event where we'll be looking at and dealing with actual Rubin data. The beautiful image that we saw today, that data, none of us will get to actually work with or write science papers about for over a year. So this is kind of the standard. It's how things go. You get lots of data. You have to make sure that the data is of the right quality, and then it gets released to the community. So it's this data preview that's going to be essentially all we have for the next couple of months. And then after that, we'll start to get alerts when there are things that are changing or varying in the sky. But actually digging into those images and doing science with like galaxies or understanding cosmology, that's still some time away. But we will have some beautiful images and databases to look at a week from now. So please join me in thanking all of our panelists today. Thank you for coming to the Rubin First Look event at SkAI. It's been wonderful hosting you here. And as I said at the top, I really hope I get to see all of you in the future at SkAI events throughout the next several years.
Thanks, Adam and company.